So as shared previously, the average heating value of our transportation fuels is about 45,500 kilojoules per kilogram. However, for other fuels, the amount of energy that's derived from its combustion is significantly different. So for example, for ethanol, we only get about 27,000 kilojoules per kilogram. It's not nearly as efficient. Whereas on the other hand, the combustion of hydrogen produces 120,000 kilojoules per kilogram. So to determine that heating value, what we need to do is use the heats of formation of each of the compounds that are involved in the reaction. So it's basically the heat of the reaction when a compound is formed from its elements. And so to figure out what the heating value of a fuel is, how much energy you're going to get out of combusting it, you need to know, first of all, the amount and the type of fuel that's being used. Obvious. Second, we have to know the composition of the combustion products. And then finally, we have to know what are the heats of formation for all of the molecules that are in the reaction. We can then figure out how much energy it takes to break up the molecules, and then how much energy is formed upon the formation of the reaction products to figure out how much energy is derived from burning that fuel. So let's see if we can confirm that burning hydrogen does indeed produce approximately 120,000 kilojoules per kilogram. So we have the heats of formation given to us here. Now in the case of hydrogen and oxygen, there's no energy release in its formation because it just happens naturally, as opposed to when hydrogen is formed in this combustion reaction, there's a negative, meaning a release of 13,423 kilojoules per kilogram when water is formed. So the first thing we've got to do, though, is we've got to balance this stoichiometric equation that we see in front of us here. Now we've already balanced this before for hydrogen, so we'll go through it quickly. But our equations are going to be 2A for the hydrogen equals 2C. For the oxygen, we've got 2B on the left equals C on the right. And so with too many variables, not enough equations, if we set A equal to 1, we can see that we end up with A is 1, we get C is 1, and then B is 1/2. So if we just multiply everything by 2, we'll get 2 hydrogen plus the 1 oxygen yields 2 water, and then plus the heat that's being released. So to find the heating value, we're going to go through and use the table that we see below. So from our stoichiometric equation, I'm going to include the molar quantities of all of the molecules that are in the reaction. So we've got 2 moles of water, we've got the 1 mole of oxygen, and then we've got the 2 moles of water. So now we want to convert these to mass. And so we want the mass amounts of the 2 moles of hydrogen, the 1 mole of oxygen, and the 2 moles of water. So hydrogen, 1 kilogram per kilomole of hydrogen. So with 2 hydrogen gas times the 2 moles, we're going to have a mass of 4 kilograms in those 2 moles of hydrogen gas. For the oxygen, 1 mole of the oxygen gas, so 2 times 16, so we're going to get a mass of 32 kilograms. And then for the water, we have 2 moles of the water, so 2 for the hydrogen plus 16 for the water times 2, so we get 36 kilograms as the mass there. And so now what we need to do is we need to find what is the mass ratio. So we're calling that M. And so that is the number of kilograms of each of these quantities per kilogram of fuel. And so I'm going to divide everything by the amount of fuel that I have. So all my masses are always going to be divided by the amount of fuel. I'm trying to get the mass ratio with respect to the fuel. So I'm always going to get 1 as an answer here, because I'm always going to divide that amount of fuel, the mass of the fuel, by itself. And then I have 8 kilograms of oxygen per kilogram of fuel, and then I have 9 kilograms of water per kilogram of fuel. Then we're going to take these mass amounts and we're going to multiply them by the heats of formation of each of these molecules that we get from a table of values. So we've got those up here. So these are found in the laboratory. It's measured how much heat is produced. And so I already talked about the hydrogen and oxygen having 0 heating values because of their natural formation. And then for water, when water is formed in a reaction, we get per kilogram 13,423 kilojoules. So now I'm going to multiply these two rows because I'm going to figure out how many kilojoules per kilogram of fuel are being produced. If we think about the units, so we've got kilograms of whatever the item is divided by kilograms of fuel. If I multiply that times kilojoules per kilogram of that particular item, the kilograms of the particular molecule are going to cancel out, and so then we're going to be left with kilojoules per kilogram of fuel. So 1 times 0 is 0, 8 times 0 is 0, and then 9 times that negative 13,000. If we round off to 3 significant figures, we're going to get negative 121,000 kilojoules per kilogram of fuel. And so then our last step to figure out the heating value of our fuel, in this case the hydrogen gas, we're going to subtract. We're going to take the heat that is required from the reactants minus the heat that is released from the products. So in this case, since it was just hydrogen gas and oxygen gas, our reactants is 0 plus 0, and then for the products, we're going to subtract just what's produced from the formation of water, the negative 121,000 kilojoules per kilogram of hydrogen, and so we end up with a heating value of 121,000 kilojoules per kilogram of hydrogen. And so that is confirming what we were told at the outset, that we should be getting around 120,000. So in our second example, we have a little bit more going on here since we are burning ethanol. So we've got that here. And again, from experimentation and previous knowledge, the heating value of ethanol as a fuel is about 27,900 kilojoules per kilogram. So we're going to try to confirm that here. So we've got to balance our stoichiometric equation here. So I'm going to set up my system of equations. So for the carbon, we've got 2A equals just C on the right-hand side. For the hydrogen, we've got 6 hydrogen because we've got the 5, and then one more makes 6 times A equals, then on the other side it's 2D. For the oxygen, we've got multiple spots where oxygen is present on both the left and the right. So on the left-hand side, we've got oxygen in the fuel, so we've got 1A or just A, and then plus the oxygen there, so plus 2B. And so that's going to be equal to, on the right-hand side, we've got 2C plus D. And so we've got to solve that system of equations. So if I start off with A equaling 1, that'll mean C equals 2. So if I plug in A is 1 into this next equation, we get 6 equals 2D, or D equals 3. And then finally, that means we can plug in 1 for A plus 2B equals 2 times 2 is 4 for the C, plus 3 for the D. And so we've got, if we subtract 1 from both sides, 2B equals 7 minus 1 is 6, or B equals 3. So now we have our balanced equation where we've got 1 ethanol plus B is 3, so 3 oxygen yields 2 carbon dioxide and 3 water plus the heat. So I'm going to take those molar quantities and I'm going to include them in this top row of our table. So I've got the 1 of the ethanol, I've got 3 of the oxygen, I've got 2 of the carbon dioxide, and then I've got 3 of the water. So we now need to convert those to masses. So for the ethanol, we can calculate out that the molar mass is 46 kilograms. For the 3 moles of oxygen, it's going to be 3 times 32, so 96 kilograms per kilomole. For the 2 carbon dioxide, 44 is the molar mass of 1, so 2 times 44 is going to give us 88 kilograms of carbon dioxide. And then water is going to be 3 times the 18, so 54 kilograms of water. So now we're ready to take all of these masses and divide by the mass of the fuel. So again, that's always going to be whatever we have here for the fuel. So we're going to divide everything by 46 kilograms. So our answer for this first one, of course, is 1, since we're dividing 46 by itself. 96 divided by 46, I'm going to get 2.09. 88 divided by 46 gives us 1.91. And then 54 divided by 46 is 1.17. So we can just push buttons on a calculator to generate those results. Now we need our heats of formation for all of these compounds. And so we can just pull these from a table of values. I've got them provided for us up here. So for the ethanol, it's negative 5771 kilojoules per kilogram of the fuel. For the oxygen, again, it's 0. For the carbon dioxide, it's negative 8942 per kilojoule, or kilojoule per kilogram of carbon dioxide. And then finally for the water, we saw this in the last one, negative 13,423 kilojoules per kilogram of water. And so now I'm going to multiply all of these mass ratios. Remember, these are all the kilograms of the actual compound per kilogram of the fuel. So when I multiply, the kilograms of each of these items cancels out, and we're left with the kilograms of fuel on the bottom with kilojoules on the top. So when we multiply, so here we're going to get negative 57, and if we go to 3 sig figs, we get negative 5770. Here we get 0 times 2.09 is 0. 1.91 times negative 8942 gives us negative 17,100. And then finally for the water, 1.17 times the negative 13,423 gives us negative 15,700. And so now we're going to take the sum of the reactant side minus the sum of the product side. So we're going to have negative 5770 plus 0. So that's what it takes to break apart these compounds. And then the release that's in the formation of the carbon dioxide and water is negative 17,100 plus that negative 15,700. So we subtract reactants minus products. And so if we go through that, we're going to find a result of approximately 27,000 kilojoules per kilogram of the ethanol.